In this video, we're going to be talking about a concept in physics known as the work-energy theorem. And actually, there are two videos in this series. In this first video, we're going to be just focusing in on how the work-energy theorem applies to a specific type of energy called kinetic energy. But before we get to work and energy, we need to reconsider what we know about forces in the context of Newton's laws of motion. Newton has these three laws of motion that were the basis for what we've been studying in dynamics and how objects are accelerated by forces. The first law of motion identifies that an object that's at rest remains at rest. An object that's moving will continue moving in a straight line and at a constant speed. And in order for either of those conditions to be changed, there has to be an external net force acting on the object that causes it to change its motion away from moving in a straight line at a constant speed or away from being at rest. If I were to state Newton's first law of motion mathematically, it would look something like this. If the net force on an object is zero, that means that the acceleration of that object is zero. Now, keep in mind what I'm not saying here. I'm not saying that the velocity is zero or that the object is not moving. If the object is moving and there's no net force, it's just going to keep moving at the same rate and in a straight line. However, if there is a net force, if the net force is not equal to zero, then there's going to be an acceleration. And that acceleration can be positive or negative, depending on if the net force is positive or negative. And the acceleration is going to be in the direction of the net force. Newton's second law of motion is typically stated mathematically from the outset. And it's this equation. The net force on an object equals the mass times the acceleration of an object. So this tells us that when we apply a force to an object, the amount of acceleration is going to be proportional to the mass of the object. It's more difficult to accelerate a more massive object. It takes more force to do so compared to a less massive object. Now, you'll notice that both of these laws of motion refer to a single object. Newton's first law of motion is referring to whether or not there is a net force on a single object. In Newton's second law of motion, there's only one mass involved, so there too we're just referring to one object. And that was perfect for our study of dynamics. Because you'll remember, as we were studying dynamics, we could only study one object at a time. Every time we drew a free body diagram, our free body diagram was just representing all of the forces acting on a single object, a single mass. But Newton's third law of motion is a little different because it actually involves more than one object. It allows us to explore the interactions between different objects. And that's what we're going to be doing in this lesson as we consider the work-energy theorem. We're going to be considering how objects interact with one another. Here's Newton's third law. The third law of motion states that for every action force, there is an equal and opposite reaction force. What does this look like mathematically? Well, I can write an equation just based on this sentence. Here I have an action force and a reaction force. So to make sense of this, let's consider that you have two objects, object A and object B. And what are the characteristics of an object? Well, an object is something that has mass, and in this case, we're having two objects that are interacting with each other. And let's simplify things further. Let's say that you are object A, and you're exerting a force on object B. You're pushing something. Well, what Newton's third law of motion says, if you push something with a certain amount of force, you are object A applying a force to object B, that object B is going to apply an equal and opposite force back on you. The greater the force you push with, the greater the force you feel pushing back on you. And you can experience this anytime you push a sufficiently massive object. You can feel that a reaction force is being pushed backwards on you. And Newton's third law of motion holds true in any interaction. Anytime we've ever had a force, anytime you've drawn a free body diagram and there was a force that you put into that free body diagram, we could have drawn a second free body diagram that showed a different object, whatever object that force was coming from, there would be an equal and opposite force being placed back on that other object. Now, to make sense of this, let's take a look at an example we've seen in the past. Let's watch a video of a crash test of a car against a wall. Here's the video, and we have this abrupt crash of a car against a wall where the car is clearly applying a force to the wall, But when we studied this, we weren't talking about the force that the car was applying to the wall. We looked at the force that the wall was applying back on the car. Both of those are real forces that you could envision. Let's just take a look at what our free body diagram would look like for the car when we looked at this the first time. So here I have the car, and what forces are acting on the car? Well, I've got this huge reversed force acting from the wall, pushing backwards on the car. Then I also have some other forces. I have this normal force from the floor pushing upward on the car, and then the force of gravity, which is the earth applying a non-contact force to the car. Next, we can do that thing where we identify the agents for each of the forces that are acting. So I have my contact forces first, and I'm going to identify that I have the normal force of the wall is the wall acting on the car. The agent is the wall, the object is the car. The normal force from the floor is the floor acting on the car. And then lastly, the one non-contact force is gravity. That's the earth and the earth's gravitational field on the car. Now notice that all of these forces say that they're acting on the car, on a single object. And that's the basis for me drawing a free body diagram with three forces acting on a single object, because all of the agents of these forces are directing their forces on the same object. With action-reaction pairs, though, my forces are now going to be directed at different objects. They're no longer going to be directed at the car. I'm going to be exploring the forces that the car is exerting on other objects. Now, my car is my agent, and the previous agents are going to become the objects. Let's take a look at what that looks like. So I'm going to have first a contact force. That's a reaction force of the action force that was the normal force of the wall on the car. I'm going to have the reaction force of the car applying a force to the wall. And you can envision that that's happening. As you look at the picture in the top left, notice that the car is clearly applying a force to the wall. Now, the car is accelerating because of the force of the wall on the car. The wall is so massive because it's attached to the ground that it actually has the ground's mass with it as well. The wall is so massive that it is barely being accelerated to the left by the car. If I were to draw a free body diagram for that reaction force, what would it look like? Well, I would need to have the wall as my object and the car as my agent now. So this is a force being applied to the wall, and notice that it's equal and opposite to the action force. It's in the opposite direction, but of equal magnitude to the force that the wall is exerting on the car. So I'm just going to circle these two in blue as an action-reaction force pair. All right, what about the floor on the car? What's the reaction force involved in that one? Well, I'm going to have a force of the car on the floor. Now, it doesn't necessarily have to be the same kind of force. It's not really a normal force that the car is pushing on the floor, because we don't think of the car as like a surface that's pushing downward. So I'm just going to call this an applied force. The car is applying a force to the floor. All right, so let's just make sure this is an action-reaction pair. Did I switch my agent and my object? Well, for the floor on the car, the agent was the floor, the object was the car. Here I have the car as the agent acting on the floor as the object. Yes. And are they equal and opposite? Well, if I draw this out, notice it's in the opposite direction, but equal magnitude to the force of the floor on the car. So these are an action-reaction force pair. And then finally, for my non-contact force, let's just think this through. Before I had the earth acting on the car through gravitation, does the car exert a non-contact force back on the earth? Believe it or not, yes, it does. And that force it exerts on the earth is equal and opposite to the force that the earth exerts on the car. Oh, wait a second. Then why doesn't the earth accelerate toward the car when the car is like in the air above the earth? It's because the earth is so massive. It does accelerate theoretically, but its acceleration is such a small order of magnitude compared to the acceleration of the car toward the earth, because the car is such a small mass compared to the earth, it's not even noticeable. It's negligibly small. But there is an action-reaction force pair anytime there's a gravitation force. When you jump into the air and you're in the air above the Earth exerts a gravitational force on you to pull you downward, and you actually do exert a gravitational force on the Earth, pulling it upward a tiny, minuscule, insignificant amount, but it's there. So I'm going to circle these as an action-reaction force pair as well. Okay, so now we've looked into what makes forces action-reaction forces according to Newton's third law, and I'm just going to repeat any force, every single force that we've been studying so far in physics. Anytime you drew a force in a free body diagram, we didn't talk about it yet, but there was an action-reaction pair going on. So any force you drew as an action force, there was a reaction force with a different free body diagram that you could have drawn that had opposite direction but equal magnitude to the force that you were drawing. All right, let's take a look at another video of a collision. What's different in this collision? Well, in this collision, we have a car that's at rest and then another car that's moving from behind it. Notice that both of our objects are moving after the collision because we're not crashing into an immovable wall here. We're crashing two objects together that are both pretty much the same mass. So because they have similar masses, they're both going to be moving. One is going to be accelerated forward, the other is going to be accelerated in reverse. And we're going to picture that first collision angle where we had the car being ran into from behind, where the cart was moving in from the left. I'm just going to refer to the object that's doing the colliding as the cart, and then the object that's a car as the car. And here's what this looks like. So I had that car. In the first image, the car was just sitting there pointing toward the right, and the cart came up from behind it from the left, and the cart collided with the car and applied a force to it, accelerating it to the right. Now, there were other forces acting on the car as well. There's normal force of the roadway below it and gravitational force of the Earth pulling downward. I'm also going to draw a second free body diagram because with Newton's third law of motion, I have to have two separate free body diagrams. And there were forces that were acting on the cart as well. Now, how is this different from what we looked at before? Before, we were looking at agents like the wall. And we didn't really draw a free body diagram for all of the forces that were acting on a wall because we kind of consider the wall is attached to the Earth. It is this immovably large mass. Here, I'm going to draw the free body diagram for the forces acting on the cart because the cart is significantly accelerated in its collision with the car. And what are the forces acting on the cart? Well, I have a force applied by the car. I'm going to call that applied force number 2. I have gravitation pulling downward, and I have a normal force pushing upward. Now, in my free body diagram, I'm assuming just from the drawing that the cart is less massive than the car. I don't know for sure that that's the case, but I've drawn those forces accordingly. Now, as I look at these two diagrams, is there an action-reaction force pair in these two diagrams? Are there multiple action-reaction force pairs? Think about that question. See if you can answer that. Well, let's just consider the forces that are acting on the car. Okay, we'll call it the action force will be the cart crashing into the car, applying a forward force on the car. I'm going to have a reaction force that switches my object and my agent. So I would say that the reaction force is the applied force number 2, the car on the cart. But is this an action-reaction force pair? Well, let's consider what it takes for two forces to be action-reaction force pairs. First of all, the agent of one force has to be the object of the other. Cart on car, car on cart. And then vice versa. The object of that force needs to be the agent of the other, if we're talking about that first force. I can clearly see that happening here. The agent and the object are switched between the action and the reaction force. Well, what else has to be true? It also has to be true that the forces are equal in size and opposite in direction. Let's look at force applied 1, that's the cart on the car, and force applied 2, the car on the cart. Are those forces equal in size? Yes. But are they opposite in direction? Yes, they are. So this is a valid action-reaction force pair. Hey, when I have two interacting objects, the cart and the car, how many action-reaction force pairs am I going to find in this free body diagram? And the answer to that is just one. because the car and the cart are just interacting in one way. They're colliding with one another, and they're exchanging force in that one way. Their normal forces aren't being exchanged. The gravitation force between them and the earth is not being exchanged. I guess technically you could think if you were jumping on the earth and applying a downward force to the earth and the earth was applying upward force to you because you were jumping, you could consider that there's another action-reaction force pair, a non-contact version, where you are applying a gravitational force to the earth and the earth is applying a gravitational force to you. There will be some odd situations like that, but in most cases, and especially in the case of a collision like this, where we just have an applied force from one object to another force, there's just one action-reaction force pair between the two free body diagrams. Well, then what are the reaction forces to the other action forces that are acting on the car, the gravitation force and the normal force? Well, I can identify those, and it starts by listing out the contact forces and non-contact forces acting on the car, and then I'm going to consider what the reaction forces are for each of the forces. So when I consider the object and agent for the road on the car, the agent is the road, the object is the car. For there to be a reaction force, there needs to be one that switches the object and the agent, the force of the car on the road. And then for gravitation, same thing. I need to switch around the object and the agent. Instead of the earth on the car, it's the car on the earth. And then I can draw the equal and opposite vector. And notice that each of these is its own free body diagram. So I have a free body diagram with the road at the center because it's its own mass that has forces applied to it, and with the earth at the center. And now I have the action-reaction pairs shown for all of the forces in my car free body diagram. Notice that I had to draw a separate free body diagram for each of the reaction forces because there's two objects that are interacting here. And when I have objects that are interacting, I need to draw separate free body diagrams. I can't include more than one object in a single free body diagram. That is still true even now that we're dealing with Newton's third law of motion. Okay, now what am I going to use this for? How do I come up with an application of these equal and opposite forces? Well, there's all sorts of real world applications of this. You use this all the time. You're very used to using Newton's third law of motion in your everyday life because you know it applies even without thinking through how it applies. You use this to walk. Every time you walk, you apply a backwards force of friction to the floor so that the floor applies a forward force that accelerates you forward so that you can move. You use this when you jump. When you jump, you apply a downward force with your muscles to the ground. There's an applied force to the ground, and the ground applies an equal and opposite normal force upward on you that pushes you away from the ground. You use this when you play sports like soccer and you plant your foot before you kick the ball, because you know that as you apply a force forward on the ball, especially if you kick it with a sufficiently large amount of force, you're going to be pushed backwards from that forward force, and you need that frictional force of your foot against the ground to hold you steady. You apply Newton's third law of motion all the time, even though you typically don't think about action-reaction force pairs. Your brain has just internalized it, so you don't really have to think it through in order to apply it. But now let's think about this in a more mathematical sense. And again, we're dealing with multiple objects here. Multiple objects that are interacting with action-reaction forces. That's what sets this aside from our study of dynamics, where we were thinking about how Newton's first and second law helps us predict how objects are going to accelerate when forces are applied to them. Now we're thinking about multiple objects interacting through action-reaction forces. And there are three possible outcomes. And these are going to look familiar because these are the three possible dynamics outcomes, because these are the three things that can happen when you apply a force, whether it's an action-reaction pair or whether it's the same sorts of forces that we had applied to a single object. There's three possible outcomes. Okay, so let's just picture a car and the forces that are acting on the car in a free body diagram. Let's say the car is parked. Are there any forces acting on a parked car? Well, absolutely there are. There would be a gravitational force and then a balancing normal force. If all forces are balanced Even when we have action-reaction pairs, if all of the forces are balanced, there's no motion. Now, do we have any action-reaction pairs going on? Well, not in this diagram, we don't, but we do have action-reaction pairs anytime there are forces. So the normal force, which is the force of the road on the car, has a reaction pair of the force of the car on the road. And gravitation, just like before, the force of the earth on the car, there's also a force of the car on the earth. But all of the forces here, even the reaction forces, are balanced, so there's no acceleration whatsoever. I could also have a situation like this. Let's say I have a frictional force of the tires pushing backwards on the ground, which is propelling the car forward. Now, you heard me mention the action-reaction pair there. The frictional force pushing backward on the ground propelling the car forward. And actually, this frictional force in the diagram is the ground pushing on the car forward. But let's say I also have an air resistance force that equals the friction force. What is the motion going to look like here? Well, the car is moving, but it's just moving at a constant speed because all of the forces are balanced. That's the second possible outcome if I have forces acting on an object. If my forces are balanced, I could have motion at a constant speed. And then the third possible outcome of forces acting on an object, let's say my air resistance force isn't balancing my forward force acting on the car. What's going to happen then? Well, the car is going to accelerate forward because there are unbalanced forces. Now, it's important to note, as I've mentioned this entire time, balanced forces are not action-reaction pairs, and people often will get those confused. Balanced forces are two forces or more, it could be more than two forces, acting on the same object in the same free body diagram. Action-reaction pairs necessitate more than one free body diagram because we have more than one object. I just wanted to make that note so that you understand that normal force and the gravity force are not action-reaction forces. They're balanced forces. That's something different. To have an action-reaction pair here, I would have to have at least one more free body diagram like this one. So this is going to give me one action-reaction pair with one of the forces in my original free body diagram. And in this case, the road is the object and the car is exerting a force on the road, a frictional force by the tires pushing backwards on the road. You see that FF1 and FF2 are an action-reaction force pair. All right, now what am I going to do with these three possible outcomes? Well, we're actually going to ignore the first outcome because it's not very exciting for what we're talking about. Because remember, we're talking about the work-energy theorem here. We talked a lot about Newton's third law. We're ready to now dive into a mathematical analysis based on Newton's third law. But in order for us to consider the impacts of Newton's third law of motion, we have to have objects that are actually moving, actually covering a distance. Now, honestly, if forces are balanced, there are still action-reaction forces, but the work-energy theorem is really boring if there's not motion. So we're only going to consider when forces are balanced and motion is at a constant speed, or if forces are unbalanced and we have an object that's accelerating. Okay, so we've identified that our objects are moving either at a constant speed or with acceleration. If object A, let's say that that's the car, interacts with object B, the road, over a certain distance, it has to be true that the distance that the force of A on B is exerted, that's that force of the car on the road, it must be equal to the distance of the force of B on A, the force of the road on the car. Think about that. If you have a car driving over a certain stretch of road, applying a force to it as it moves over a distance, and let's just say that the car is accelerating on the road. So it's moving a certain distance and it's moving at an accelerating rate, is covering more distance per unit of time. Does it have to be true that the distance that the car is applying a force to the road is the same as the distance the road is applying a force to the car? It has to be the same distance that they're in contact because the car is covering the same distance along the road as the road is experiencing the distance that the car is covering. It's even hard to say it. It's just intuitively true when you think about it that the car's distance in contact with the road has to be the same as the road's stretch of distance that it was in contact with the car. Okay, so what I'm going to do is I'm going to take our Newton's third law equation, I'm going to add another variable to it. And because the distance is the same, I could just multiply both sides by distance, and mathematically, I've done nothing wrong here because I'm multiplying both sides of an equation by the same variable. Okay, now let's do some mathematical manipulation of this. I'm just going to note our Newton's second law equation that the net force on an object is the mass times the acceleration. And I'm going to replace my force on the left with ma. And because we're talking about object A acting on object B, B is the object that the object A is acting on. B is the one that's actually receiving the force. So it's the mass of object B that matters. So the mass of B times the acceleration of B times the change in distance equals the opposite of the force of object B on object A times its change in distance. And the change in distance has to be the same on both sides. So you can still see this is just Newton's third law. I've just replaced one of the forces with ma. All right, let's further expand this. I have this kinematics equation that helps me envision what's happening with acceleration. So I know that this equation from kinematics is true if I have an object that is increasing in speed because of an acceleration. I have this relationship between the speed, the acceleration, and the distance. I'm going to rearrange this equation, though, to solve for acceleration. Because I have acceleration in that left-hand term now, I want to replace that with terms that include velocity and distance. And this is what it looks like when I rearrange that equation to solve for acceleration. You can check my math and see that this is actually the equation with acceleration on a side by itself. Now, what I'm going to do is I'm going to combine the third equation in this column with that final equation. I'm going to substitute in this equation for acceleration into that third equation. And when I do that, this is what I get. Notice that I just did a simple substitution for acceleration. All right, the next thing I'm going to note in this equation is that I have delta d on the left in the denominator and in the numerator on the outside of the parentheses. So I can go ahead and cancel that change in distance term. That's going to be handy in writing an expression that looks a lot neater than this one currently does. And then here's what I'm going to do in the next step. I'm going to distribute that mass of B into the expression in parentheses. That's going to just be multiplied by both of the terms in the numerator. Then I'm going to also distribute the divided by 2 in the denominator. The delta d canceled out, but I can distribute that divided by 2 by multiplying both terms by 1/2. You'll see that in just a moment. The other thing that I'm going to do, I'm going to go back up to that expression at the very top of this page. That's the Newton's third law of motion expression. I'm going to note that negative FB on A is equal to the force of A on B. And I have that negative FB on A expression on the right-hand side. I would really prefer for that to be a positive expression. And I would really prefer for it to be the force on B because I have the mass of B on the left-hand side of this. So I'm going to go ahead and replace that expression right away as well. So we're going to see that distribution and that replacement of the term on the right here. Okay, so take a moment, make sure that there's no hanky-panky going on here, that this all looks correct. And then what I'm going to do is I'm going to add the negative, see that negative 1/2 mb vox squared term in the middle there? I'm just going to add that quantity to both sides so that everything is positive. Then I'm just going to flip the equation around so that what's on the right-hand side of the equal sign is on the left and what's on the left is on the right. So the key is everything's going to be positive when I add that expression in the middle to both sides. And you'll see that this is the exact same expression. All I've done is I've changed the signs by adding 1/2 mb vox squared to both sides. And in addition to that, I've switched the sides of the equal sign to get this expression. Now, why did I do this? This is a very useful expression that I have on the page here. It doesn't look so useful, but what I can do is I can define some terms here. I'm going to say that this term 1/2 mvx squared is equal to kinetic energy. And if it has a 0 in it or an O, that's the original kinetic energy. If it doesn't have a 0 or an O, that means it's the final kinetic energy. Okay, I'm also going to define this. Force times distance equals work. Okay, so anywhere I have a force times the delta distance, I could replace it with a W for work. And I'm just going to replace any 1/2 mv squared with K and F delta D with work. And we'll talk about why I define those that way in just a moment. And we'll see that I have these two very simple expressions. Here's the first one. My original amount of K, kinetic energy, plus the amount of work that's done is equal to my final amount of kinetic energy. Or another way to think about that, if I rearrange this, work is equal to final kinetic minus original kinetic. And anytime I have the final amount of something minus the original, that means it's the change in that thing. So work is the change in kinetic energy. Okay, let's talk about it. That seems like I did some hocus pocus there with defining terms and replacing things. So let's talk about those terms on this next slide. We're going to talk about work being equal to force times delta distance. We're also going to talk about kinetic energy equaling 1/2 mvx squared. But wait a minute, let's just take a look at that kinetic energy term for a second. I have that x in there. And the reason I have that x in there is because that has to be one-dimensional. The kinetic energy that I'm expressing with this relationship is in the same direction as the force, and everything has to be in a line. Was there a cleaner way for me to express it so I don't have to have that subscript x in there? Let's consider a real-world situation where you would apply a force at an angle, and we would have a different force direction than our line of motion. So here's the direction, the line of motion that a lawnmower moves when you're pushing a lawnmower like this. But when you're pushing a lawnmower, you don't get down on the ground behind the lawnmower and push it straight across and sort of do belly crawl behind it to move it across your lawn. You push down the handle. That means that you're applying a force at an angle down the handle. And if I were to draw where that force was actually acting on the lawnmower, I'm just going to move that force to the center of mass of the lawnmower. This would be the applied force being pushed onto the lawnmower. Then I have some other forces. I have the gravitational force pulling downward, normal force pushing upward. We'll say that we're rolling this lawnmower over concrete right now. We're not actually mowing the lawn with it yet. So there's not any significant friction force. But notice that my downward angled force that I'm applying to the handle is pushing somewhat downward and somewhat to the right. I want this lawnmower to accelerate toward the right, but I'm wasting some of the force. Now I'm forcing that normal force to compensate for some of the force that I'm pushing downward. Well, here's the thing. Not all of the force is doing work on the lawnmower, only the part of the force that's in the direction of motion. And anytime you have a force that is at an angle compared to your direction of motion, you have to find the part of that force that's doing work, using the angle between the force and the direction of motion. So how do I do that? Well, here I've got my x and y coordinate plane set up so that it's at the start of the applied force. Okay, notice that my applied force is the origin of that vector is where I'm setting the origin of my xy coordinate plane. And then I'm going to draw the angle between the x-axis and the applied force. That x-axis represents the direction of motion. So the actual lawnmower is moving horizontally, but I'm applying a force diagonal. And here I have a theta. And what am I going to do with that theta? Well, I could use that theta to calculate how much force is actually being applied in the direction of motion. I use that theta to find F applied x in the x direction. I'm just going to note something here too. The correct way to do this is to set this up exactly like I did, where your force vector is, the beginning of that force vector is at an origin of an xy coordinate plane, and then theta is from the x axis, as long as your motion is along the x-axis, theta is from the x-axis to the force. That theta technically, you don't have to do this, but I'm just going to note this, that theta technically is a negative angle. And I would plug it into my trig functions as a negative angle, and that's going to give me the correct positive or negative value for the x component. And I see this x component is pointing toward the right, so it's going to be positive. and this would give me the correct value of that. If that value was negative, that tells me that it's opposite the direction of motion, and that's something significant to note as well. Okay, so I'm just going to note that the force applied in the x dimension is equal to the applied force at an angle times the cosine of theta. That's always going to be true as long as you always measure the theta between the direction of motion and your actual applied force. What I'm doing here is, in effect, in my free body diagram, I'm replacing my diagonal applied force with a horizontal applied force. That's the one that's important. That's the one I'm actually calculating with the cosine. And then there's also going to be a vertical applied force that I would calculate with the sine, but I don't need to worry about that here. I'm only interested in finding the amount of force that's in the direction of motion. I'm going to do that with cosine. Now I'm going to go back over to my equation on the left. I'm going to adjust things in my work equation so I can get rid of that one-dimensional x in my kinetic energy equation. I don't want that in there. And here's how I'm going to adjust it. I'm just going to replace it with the expression we just developed. So the force times the cosine of theta, that's the theta between the force and the direction of motion, is going to give me the amount of force in the direction of motion. And I'm going to further adjust this to just clean it up and put the cosine of theta at the end. Force times distance times the cosine of theta is going to give me the amount of work. This cosine of theta is really multifunctional. So I can use this if I have forces at an angle to find the amount of force that's in the direction of the work, or if I have a force that's in the opposite direction as motion, technically that's a 180 degree force, and the cosine of a 180 degree force is -1. Also, what if I have a force that's perpendicular to motion? Like notice that the normal force is perpendicular to motion? Well, if I were to try to find the amount of work being done by the normal force, I would have to include the cosine of 90 degrees, and the cosine of 90 degrees is 0. Any force that's perpendicular to the direction of motion can't do any work because it's not pushing in any amount in the same direction as motion. Okay, so these are the equations I'm going to use. I'm going to readjust that kinetic energy equation to get rid of that subscript x, and now I have my actual equations for work and for kinetic energy. Now, let's talk about what these terms mean. We have to define these things. I've been using the word energy a lot. What in the world is energy? Energy is actually pretty complicated to define. The very best definition I've found of energy is it's the ability of an object to cause a change. Okay, so notice what I say, the ability of an object. So it's caught up in a single object. We would be able to identify the energy of a single point like we would a free body diagram. And it's a potential, right? It's the ability to do work. So the object isn't doing work right now, but it could do work. It could cause a change. What is kinetic energy? Well, that's actually just energy that expresses itself in the velocity of an object. Anytime an object has velocity, it has the ability to cause a change. The more velocity it has, the more potential to cause change. And because I'm using the word object, I'm also tying in the idea of mass, because an object has to have mass for us to classify it as an object. So mass also plays into kinetic energy. The more mass something has, the more kinetic energy it has as well. You can picture a car slowly rolling through a parking lot. The reason that there's slow speed limits in school zones, we force cars to move slowly because they don't have as much energy. They have the ability to change their speed fairly quickly, and if they do run into somebody moving at a pretty slow speed, there's probably not going to be that severe of an injury. However, cars on a freeway that are moving much more quickly, they have a lot more ability to cause change because of their higher velocity. So it's much, much more dangerous. That's why pedestrians aren't allowed on the freeway, because if you did get hit by a car moving at freeway speeds, it would be catastrophic. And then finally, what is work? Work occurs when there's an interaction between objects and an energy exchange occurs. Work changes the amount of energy in an object. And we'll see that once again when we look at our equation that we just developed on the previous slide. Let's talk really quickly about what we measure energy in. It's measured in a unit known as a joule. And what is a joule? Well, let's just take a look at our equations for energy and for work. Our work equation is force times distance times the cosine of theta. Force has units of newtons. Distance is standard units of meters. And cosine of theta doesn't have any units. It's just a ratio. So I have newtons times meters. And it's important to note here that these newtons and meters in this unit label for work are in the same direction. Newtons times meters. Well, what is a newton? A newton is a kilogram meter per second squared. Okay, so newtons are kilograms meters per second squared, and when I multiply that by meters, I get units of kilograms meters squared per second squared. And that's what a joule is. Now, honestly, you can make more sense of this if you expand it out and don't combine all the terms. Kilograms times meters per second squared, so a mass times an acceleration times the distance over which that mass times acceleration is occurring, times meters. And a kilogram meter per second squared times meters, or a kilogram meter squared per second squared, is the same thing as a joule. That's what the defined term of joule is. So just like a newton is a kilogram meter per second squared, a joule is a kilogram meter squared per second squared. What about energy? So I have this 1/2 mv squared kinetic energy expression. What are the units of that? Well, it's going to have units of kilograms times meters per second, and then that meters per second label is squared entirely. So I have to distribute that squared to the numerator and denominator, and that's obviously going to give me kilograms meters squared per second squared, which is the same unit label as joules. So work is measured in joules, energy is measured in joules, but that would make sense because in order to add or subtract energy with work, they have to, when I add or subtract two values, they have to have the same unit label for me to add or subtract them. So it makes sense that work and energy would have the same units. And now that we know the units for energy, let's talk about the work-energy theorem. We've arrived at the point of the lesson, the work-energy theorem for kinetic energy. Now we know the definition of energy. The definition of kinetic energy is just energy expressed through velocity. And we know work is what changes energy. And we've already derived this equation. The original amount of kinetic energy plus the work done on our object is going to equal our final amount of kinetic energy. And what are we saying here? We're saying that work must be done on an object to change its kinetic energy. That's the work-energy theorem for kinetic energy. And actually, the amount of change of kinetic energy is the same as the amount of work done. That work could be positive, that would increase the speed and increase the kinetic energy, or it could be negative work. Another way to think about that is our object could do work on its surroundings, which would cause a decrease in kinetic energy or decrease in speed. We've seen examples of both of those happening. Forces in the same direction as motion accelerating an object, or forces in an opposite direction of motion decelerating. Now, why is that force relevant here? Well, work is just force times distance. So we have a force being applied for a distance in the same direction of motion, increasing our kinetic energy, or a force being applied for a distance opposite the direction of motion, which is decreasing our kinetic energy. But that's the work-energy theorem. If there is no work, if the work value is 0, that means that whatever kinetic energy I have before an interaction is the same as the amount of kinetic energy after the interaction. And what that means is the interaction, whatever it is, must not be applying a force over a distance. Because if there was a force being applied for a distance, there would be a change in kinetic energy. For there to be no work, there must be no force applied for a distance. Maybe there is a force being applied, but it's being applied perpendicular to the direction of motion, and therefore the kinetic energy is not going to change. All right, and that's the work-energy theorem for kinetic energy. We've defined the terms energy and work, and we're going to carry those definitions forward to the next lesson where we apply this to a different type of energy known as potential energy.